Hi students, Professor Nugent here. In this video we're going to discuss feasible GLS. The functional form of heteroskedasticity is often not obvious, so it can be often very difficult to think of, what to use for that function of h with which to estimate weighted least squares. So what are we to do? Well, we can model h. We can use data then to estimate the unknown parameters in the model. We can get an estimate of h hat, so a fitted value of h, and then use the h hat instead of h in the GLS transformation, and this procedure is known as feasible GLS. So let's look at this procedure in a little bit more detail. We have that, we can write that the variance of u given x as the following. Sigma squared times exp of delta naught plus delta 1 x1 through delta k xk, where h of the x's is equal to the exponent of delta naught plus delta 1 x1 through delta k xk. And we use this functional form, we're using the exponential function because this exponential function ensures that the fitted value h hat and the variance will be positive, because we need that, variance is a positive number. If we don't use this functional form, if we were to use something just like a regular linear function, then we do not have this assurance that the fitted value h hat will be positive. And so you can end up with some funky results. So we're going to use this functional form because we have that assurance that the fitted value h hat, the variance is going to be positive, and it's also quite flexible. Alright, so we can use data to estimate the parameters. The model that we are estimating is the following. U squared is equal to sigma squared times exp of delta naught plus delta 1 x1 through delta k xk, and we're going to bring in this extra term for to make the analysis a little bit more simple. We're going to multiply this times the term v, which has a mean 1 and is independent of x, so that when we log linearize this thing, we take the log u squared is equal to alpha naught plus delta 1 x1 all the way through delta k xk plus some error. And the error term, let's just write e. E has a mean of 0 and is independent of the x. So because e is independent of the x, has mean of 0, the Gauss-Markov assumptions are satisfied, so we can get unbiased of the estimates of these coefficients using an OLS regression of the log of u squared on these things. And what we're going to do is regress log of u squared hat. Really what we'll do is use log u squared ui squared hat. We'll regress this on x1i through xki. We'll then obtain fitted values for the observations I equals 1 through n, call the fitted values gi hat, and then solve hi hat is equal to exponent of gi hat. Finally, we use weights one over hi hat to transform the equation. So we have the sum from I equals 1 to n of yi minus b0 minus b1 x1 all the way through bk xk over hi hat, and this is transformed into the sum from I equals 1 to n of yi star minus b0 x0 I star minus b1 x1 I star minus all the way through bk xk I star in the same way that we discussed before. Now, some words of caution using feasible GLS. Using H, not H hat, then WLS is blue. If we have to estimate H, so using H hat, feasible GLS, FGLS, is not unbiased. It's not unbiased and therefore not blue. FGLS is, however, more asymptotically efficient than OLS. A word of caution, be careful when completing F-tests. You want to use either transformed or non-transformed equations. You would not want to do an F-test where one equation has been estimated using WLS or FGLS and another equation has been estimated using OLS. A restriction between equations where the estimates have been estimated using two different estimators cannot be compared using the F-test. Now, if the estimates are very different, if OLS and WLS very different, it's likely one of the multiple linear regression assumptions violated. Alright, it's probably multiple linear regression assumption 4, so that in this case this assumption fails in the case of functional form misspecification. So the expected value of u given x does not equal to 0, and this often occurs in the case that expected value of y given x does not equal to the model used, such as beta 1 plus beta naught plus beta 1 times x1 through beta k times xk. And if this is the case, then OLS and WLS will have different expected values and probability limits, which is a reason for having very different estimates and complicates the analysis. Stay tuned for the next video. We will discuss consequences of having the wrong heteroskedasticity function, and we will also discuss prediction and prediction intervals with heteroskedasticity.